If you take a look at the side view mirror, the rear view mirror of a car or a bike, and if you touch its surface, you will find that it is not a flat mirror. It's bulged out a little bit. It's curved. Why is it a curved mirror? Why don't we use just a normal, regular flat mirror over there? And why are the objects in the mirror closer than they appear? We're going to answer these questions satisfactorily in this particular video. So to understand or to answer this, the secret lies in understanding curved mirrors. Now, before we begin, we've already seen in a previous video one kind of curved mirror, a mirror in which the inner part is reflecting. And we call such a mirror as a concave mirror. And we saw what it does. We saw that if you were to incident parallel beam of light or parallel rays of light, then they all after reflection get concentrated at a single point called as the focus. So a concave mirror can converge a beam of light. But this time we're going to talk about what will happen if you were to make the outer surface reflecting. That's the focus of this video. What happens if you make the outer surface reflecting? So let's do that. Let's get rid of these rays and let's make the outer surface reflecting. So when the outer surface becomes reflecting, now the reflecting part is bulged out. Can you see? Before the reflecting part, so over here, the reflecting part was forming a cave. So this was called as a concave mirror. But since now the reflecting part is bulged out, we call it as a convex mirror. The word vex literally means bulging out. All right. So the question now is, what does a convex mirror do? That's what we want to figure out. And again, we'll do the same thing what we did earlier. We will shoot parallel rays of light onto this mirror, and we will use rules of reflection and see what happens to these parallel rays of light after reflection. All right, so let's do that. Let's incident parallel rays of light. Let's do that. So here they are, parallel rays of light. And we chose parallel rays because they are easy to analyze. It's easy to understand what your convex mirror is doing. If you choose parallel rays of light, you can choose whatever rays you want. The physics remains the same, but it's easier for parallel rays. All right, so how do we figure out what happens to the rays of light after reflection? Well, the trick is we zoom in at every point of incidence. We zoom in so much and we only concentrate on that tiny patch. We assume that tiny patch to be flat. And why do we do that? Because we know how to deal with flat mirrors. We draw a normal, then we use the rule of reflection, and then we figure out where the reflected light is. All right, so what I want you to do is pause the video and see if you can try this yourself. Just draw a rough sketch and just see if you can drop normals at every point and try to, sort of get a rough idea of what the reflected light looks like. All right, let's do that. Let me do that over here. Okay, so I'm gonna do it for a couple of places and then I'll just show you what it looks like. So let's zoom in somewhere over here. Let's go here. So if I zoom in at this point, okay, at this point, over here, notice that this, I can approximate this to be a flat mirror like this. Okay, and once I know the flat mirror is like that, the next thing I do is drop a normal. In fact, we have done this in previous videos as well. So if this is not super clear to you, you can just go back and watch that video where we did that. But anyways, we're going to do the same thing over here. So here is the angle of incidence, because this is the incident ray, and so the reflected ray will go like this. How do I know it goes like that? Because the incident angle must be the same as the reflected angle. That should remain like this. All right, let me do that in one more place, somewhere over here. Let's do over here. Let's zoom in. Okay, now if I concentrate over here, the flat mirror looks somewhat like this, oriented this way, isn't it? Again, I'm going to drop a normal. A normal means, just remember, it's a perpendicular that we draw. And now we have this as the angle of incidence. So the reflected ray will make sure that the reflected angle should also remain the same. All right, let's zoom back out. Let's go back to the original view. Let me just zoom out over here. And that's what it looks like. All right, this is not very accurate because I did not use rulers or whatever, but I've done an accurate picture. So let me just show you what it looks like for all these places. So I highly encourage you to first try it yourself. Place it all in, do it at all places and try it yourself. If you've done it, let me show you what it looks like. What it looks like for everywhere. So let me just over here. Here it is. This is what it looks like. And if you notice, you can see that after reflection, the rays of light are no longer parallel, they're all going away from each other, which means your convex mirror diverges rays of light after reflection. That's the property of a convex mirror. And in contrast, just to remind you, in contrast, when we were dealing with a concave mirror, what was happening? A concave mirror, I'm just going to show you this way, over here. A concave mirror converges a beam of light to a single point, but a convex mirror diverges a beam of light. And you know what's interesting? Interesting is if you were to backtrace these, I mean, if you were to extend these rays of light, let me just do that. If you were to extend these rays of light, then these rays of light appear to start from that same point focus that we defined earlier. And so even for a convex mirror, we can define a focus. For a convex mirror, the focus is a point from where the rays of light appear to diverge from. Okay, it's not really diverging from that point, but it appears to do that. And when we define it, when the incident rays are parallel to each other. So in short, a convex mirror, as we saw, a convex mirror diverges a parallel beam of light appearing to be from a single point focus, and a concave mirror converges that parallel beam of light to a single point. So convex mirrors can diverge rays of light. Excellent. But what's the application of this? Where can we use this? I mean, I can't think of a direct application of divergence of rays of light. I mean, where would we use that? Well, there is an application, and to understand that, we need to remember something about these ray diagrams. Remember that these rays are reversible, meaning we can just reverse the arrow marks. We can make the reflected rays the incident ray, and then the incident ray becomes the reflected ray. Why is it reversible? Well, because the rules of reflection still hold true. I mean, let's concentrate on this ray. If we were to reverse this, this becomes the incident ray, this becomes the reflected ray, and we can draw a normal somewhere over here. And when we reverse this, the incident angle becomes the reflected angle, and the reflected angle becomes the incident angle. But they're still equal to each other. The rule of reflection still is valid, isn't it? And that's why, even if I were to reverse these rays, I'll just do that, let me just do that over here. Even if I were to reverse these rays of light, rules of reflection still is valid, which means this is also a valid diagram. And this will help us understand what's the application of this. Let me just make this a little bit smaller. All right, in this reverse ray diagram, what you can see is that rays of light from various wide angles can be reflected towards you. What I mean is, say you are standing somewhere over here. This is the top view of a head, okay? I have drawn specs over here. Drawing eyes was a little difficult. Anyways, imagine you were standing in front of this mirror, and let's say there's something over here. There's some tree over here, and there's some bike over there, or something like that. Now, what's important to understand is that the rays of light from this tree and the bike after reflection can come straight towards you, which means just by moving a little bit, you can see a lot of stuff at a much wider angle that's behind you compared to what you can see with a plane mirror. So if you had a plane mirror, let me draw that over here. If you had a plane mirror, and if you had that same ray of light, I'm drawing the same ray over here, notice it would have gone down after reflection because it would have missed you. As a result, it would have missed you. But because we have a convex mirror, you can see a lot of stuff behind you. So in other words, we can say it gives you a wider field of view. You can see what's behind you at a much wider angle than what a plane mirror allows you to do. And you can actually see that in this photo that I took. This is a convex mirror. It's bulged out. The mirror is curved like this. It's a convex. This mirror was kept near a parking lot somewhere over here. And notice when you look into it, you can see at a much wider angle. You can see pretty much at this end of the road. You can also see pretty much at this end of the road. This is almost a 90 degree angle, and you can see all of it over here. Sure, it looks a little distorted, but you can see it. And so if you were to come from this side, if you're riding in a vehicle from this side, you can just look into a mirror, in this convex mirror, and you can also see what's on this side. And so based on that, you can avoid collisions and other stuff. That's why these mirrors are pretty important. They're installed a lot in these parking lots. And now we can answer our original question. It's for the same reason the side view mirrors of vehicles are also curved. They are convex. Same reason, so that when you look into it, you can see a little bit wider. You can see what's there behind you at a little wider angle than if you had a plane mirror over here. I just like to end this video now with one last thing. Why are the objects in the mirror closer than they appear? This is really interesting. So think about this. If you come back over here, let's look at this picture. If this was a flat mirror of, say, the same area, imagine you had a flat mirror of pretty much the same area. I hope you agree now that in that mirror, we wouldn't be able to see as much as we can see over here. We just discussed that, isn't it? Which means a convex mirror can fit more things compared to what a flat mirror can fit in that same area, correct? But in order to fit more things, the things have to become smaller. Think about it. If you want to fit more things in that same area, shouldn't they all become smaller, right? So things in a convex mirror, or the images in a convex mirror, look much smaller than in a plane mirror. And of course, we'll look at this in great detail in the future videos. But as of now, hopefully from this reasoning, you can understand that things in a convex mirror or images in a convex mirror are always smaller than in a plane mirror. But we don't have an experience with convex mirrors. We have experience with plane mirrors. And so when we look into these convex mirrors and we look at these small images, our brain automatically thinks that these are far away, because only when things are far away, they look very tiny. And that's why we feel that these things are pretty far away from us. For example, it looks like this truck is far away from this mirror, isn't it? But it's not. It's not really that far away. And that's why there's always a reminder over here to tell you that the objects in the mirror are actually closer than they appear. They appear to be far away because they are smaller. And therefore, there's a good chance that we might do a misjudgment over there. We might take a sudden right turn thinking that these vehicles are far away. And therefore, there's always a reminder to make sure that we take into the account. So this is pretty important when we're driving. And so to quickly summarize, when you have a curved mirror where outer surface is reflecting, we call that as a convex mirror. Vex means it's bulged out. The reflecting surface is bulged out. And if you incident parallel rays of light on this mirror, then it diverges. So convex mirrors end up diverging rays of light. And their major application is in the fact that they give a much wider field of view when you look into it.